Worksheet 16a, deflection. Simply supported beam of length L is made of material with a modulus of elasticity E and has a cross section with an area moment of inertia about the centroidal axis I, and they give us the external couple C applied on the right end of the beam C as shown here, and the x-axis and y-axis defined that way. And the question is determine an expression for the deflection of the beam as a function of a linear position x. Basically, the question asks what is y x, the deflection, and determine the magnitude and location of the maximum deflection. So what is the y max? That is the y max, and at x equal to what? Okay, so that is the question asked here. And first, we before we apply the integral deflection equation, we find out the external reactions at point A and B. So let's assume A here and B on the right, and we have that is AY, AX. Then we find that down, sum up on the force. So first, that the external, the equilibrium that we have, external reaction. External reaction. So we have the moment, sum up on the moment. For example, we want to find out at B. Then we have sum of moment about A, for example. Assume counterclockwise positive, so equal to 0. So we will have at A, so this should be by. So we have by L plus C, the couple, both are counterclockwise. So from that we have the by equal to negative C over L. And then if we apply sum of all the force in y direction equal to 0, for equilibrium we have that is AY plus BY. So from that BY we plug in that is negative C over L. So we have AY with either vertical reaction at pin A is equal to C over L. From that external reaction, we can go ahead to apply the integral beam equation. And we always start with, as you can see, the lowest one, which is the load. And Wx negative equal to EI, fourth derivative of y deflection elastic curve function. But you want here, as you recall here, in the shear and moment diagram, the slope of the shear curve equal to the magnitude of the load. Okay, so with that here, and then we also have the shear equal to the slope of the moment equal to the magnitude of the shear, and then we continue to apply the mx equal to EI y apostrophe x. So let's start with the load curve and then move integral for each as we go. So first one, we use the load curve, and the load curve here, as you can see, there's nothing for the distributed load on this body, so we can have the negative, just the load normally going down, as you can see, so put negative to represent the y, the deflection here. So equal to 0, no load, no distributed load on that beam except the couple at the end B. So load curve equals 0. Then we move the next, it will be shear curve. Shear curve. So what do we have in here for shear curve? We have the shear, the change in shear equal to area under the load curve. So it means that we can integral the area under the load curve, which is the change in shear, that is Vx. And in this case, as you can see that Wx here equal to 0, then we have that the integral of the 0, it will be a constant. And when a constant, how can we determine the constant? We set the boundary condition, use boundary condition. Boundary condition. In this case, what boundary condition is, go back to the lesson that we have here, that we have for the condition, support end condition. For example, pin at ends, you have the shear, it's non-zero, and we already know what is the reaction, vertical reaction at A in that problem, and it's non-zero, and that all of the support condition we have for each of the scenarios in this case. Because we deal with the shear, so shear is non-zero, and we already find out that the vertical reaction is non-zero, VA non-zero, and that happened to be equal to C over L from our equilibrium equation here. So that what you have is x equals 0, which is when we start up the beam at A. So we have V0, it equal to V equal to AY, with either reaction at A, and in that case it's equal to C over L, that we already find out, and that the constant happen to be equal to C1. So from that, as you can see, C1 equal to C over L. C1 equal to C over L. So what does that mean? The shear curve, V equal to C1 and C1 C over L. So it will be a constant throughout the beam, and that C over L. So what does that mean here? We can draw the moment diagram from that equation. Vx equal to C over L, so it's constant regardless of how x is. So we start at 0 with AY equal to C over L. So we have that C over L, and then the constant V always C over L, and it will be get down here negative C over L. So as you can see, with this, we don't need to learn the concept in the shear and moment diagram, but with the equation here, Vx C over L, we can be able to draw the shear diagram. And of course, you can be able to draw the shear diagram without using the integral here by AY jump up. So that what discontinuity in the shear move up AY, which is C over L, and then now distributed load make it constant, and then BY negative C over L, so it means going down, and you can see here then jump down and it's 0. So that is the shear. And now we go to the moment curve. What we can find out for the moment curve. Moment curve. Now we have what? The area under the shear curve equal to the moment, the change in moment. So what is that? Mx, if we area, basically integral of Vx dx, that is the area under the shear curve, and Vx equal to C over L, so we just replace C over L dx, and C a couple, L is the length of the beam, all are constant, we can print out. So it will be equal to C over L dx. And what does that mean? We can have mx equal to C over L x plus C2, another constant. And again, we have a boundary condition for this one. What do we have for the boundary condition at the pin A? There is no moment. Pin A, no moment, right? So what does that mean? MA equals 0 at x equals 0. Go back to the lesson note that we have here for the pins or the roller at N, MA equals to 0, and you can see that. So from that, we can here, we have the boundary condition here is M at x equals 0, which is point A, and that one equal to 0. So what does that mean? Plug in the mx, it will be C times 0 over L plus C2. So what does that mean? C2 equal to 0. C2 equal to 0. And from that C2 equals 0, plug it back. What we have for the moment curve functions, mx equal to Cx over L. So what does that mean? It varies by x, Cx over L. So start with x equals 0, then it equal to 0. So when it's a linear, if x equal to L, then plug in, you see C times L over L, it equal to L cancel out, so C. So it come here, it will be C, that's C here. And then, of course, going down to 0, because that is a couple C counterclockwise, it causes discontinuity on the moment curve and going down, right? Going down. So from that, as you can see, this is a straight line, and the function here are C at B. Then the couple is C, as you can see there. And for the moment diagram, it's 0 at A and C at the right end, and that we have the moment curve. And as you can see, with our integral, we also use the four nodes in the shear and moment diagram. We can be able to draw exactly the same for the shear and moment diagram for this problem. But that's not the problem we asking all about. The question in this case, what is the function for the elastic curve, and what is the magnitude and location of the maximum? And the next video, I'm going to continue with this problem for that.